This is my final chapter 5, section 5.6, question 329 vlog. This is finally the end of this chapter, but this is pretty much the summary chapter that goes over the final two tests that we could use to test for convergence or divergence, and those are the root and ratio test. And the first one I'm going to go over is pretty much the ratio test. Say that there's a series a sub n with non-zero terms. We can let the value p equal the limit of a sub n plus 1 over a sub n, and that's the absolute value of that in the limit. So one more time, p equals the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. So if it is in that form, once we put it into that form, if the p that we find the limit, once we take the limit, if it is greater than or equal to 0 and less than 1, then the original series a sub n converges absolutely. If the p is greater than 1, or if the p is infinity, then the original series a sub n diverges, and if p equals 1 exactly, then this test does not provide you with any information, and you should probably use some other test to test for convergence or divergence, like the limit comparison test or the integral test. But that is pretty much the ratio test. Like, it just allows you to create that ratio, find that p-value, that limit among that ratio, and then tells you whether or not the series converges or diverges. The root test is pretty much along the same lines. If the form of the series is in a root, like in a root of n, then you can pretty much use this root test, and all that says is the series a sub n, the limit as n goes to infinity of root n of this absolute value of the series a sub n. If it's the same conditions, like if p is greater than or equal to 0, then a sub n converges absolutely. If p is greater than 1, or if p is equal to infinity, then it diverges. If it equals 1, then use another test, of course. Yeah, and the root test is useful when the series has I guess like exponents or roots, like if you have like something being raised to like the nth power and you are trying to get like the limit of that, it would just be a lot easier if you use the root test. The ratio test is pretty much like the other way around. Like if you don't have a root in it and you just have like a ratio, like 3 to the power of n over like n factorial or whatever, you can very easily use that root test, like find the a sub n plus 1th term, create a ratio out of it, simplify that down using like find the limit of it, simplify that down, and it'll give you that p-value, and you can tell whether or not you would need to use another test or if it converges or diverges. And those are the two new concepts in 5.6. The rest of this is quite literally just explaining choosing a convergence test. And I feel like I have a pretty good stance on it since I have been going through each section and pretty much like rereading it or trying to understand like the methodology behind each test or series. So the first one, I guess, that I just want to get out of the way is the p series. It's just if the series is in the form 1 over n to the power of p, whatever p is, if it's greater than 1, series converges. Sorry, if it's greater than 1, yeah, the series converges. If it's less than 1, series diverges. Second one is just a normal comparison test. If the series is comparable with another series B sub n, and B sub n is greater than or equal to A sub n, for all values little n is greater than or equal to big N, which is like it's just the numbered element in the series. And if B sub n also converges while meeting those conditions, then A sub n converges as well. And pretty much vice versa. If A sub n is greater than or equal to B sub n, and those conditions are met again, where n is greater than or equal to big N, if B of n diverges, then A of n diverges as well. That's just basic comparison tests, but the divergence test, that's just where you take the limit of the series. If the limit equals 0, then it's inconclusive. If it doesn't equal 0, then it diverges. And then the integral test, if you take the integral of a series and you have the new function f of n over the domain of the integral from like capital N to infinity of the new function f of x dx and of the original series, if you find that function and it is continuously decreasing, like if you can evaluate it and it's continuously decreasing, that shows you whether both the series converge or if they diverge. The next one is we went over this too, the limit comparison test. If you have series A sub n, if you compare it with B sub n, and then you take the limit of A sub n over B sub n, if that limit does not equal 0, then A sub n and B sub n both converge or diverge. If it is equal to 0, then they both converge. If it goes to infinity, then B sub n diverges and A sub n diverges as well. So if it is, again, like if you take that limit, it should be able to tell you whether it converges or diverges. And it's, again, not too hard because you don't have to take the integral or anything. The one that we went over in 5.5, the alternating series test, if it's in the form of -1 to the nth power times b sub n, then you use the alternating series test. If b sub n plus 1, like the n plus 1th term, is less than or equal to b sub n for all like n values that are greater than or equal to 0 or 1, I think, then the series converges. If those conditions are not met, then it diverges. And the ratio test, we just went over that. You can, if it is set up in a ratio, you can set the limit equal to the series at its n plus 1th term over the a sub nth term. And if the p is between 0 and 1, it converges absolutely. If it's greater than 1, it's divergent. If it is equal to 1 exactly, use a different test. Same with the root test. If you have anything under a root, if p is in between 0 and 1, converges absolutely. Greater than 1, diverges. Equal to 1, inconclusive, use a different test. And that is pretty much section 5.6. It's just a sum up of all of chapter 5, and it shows us like the cheat cut tests, the ratio and root tests, just to tell whether or not it's convergent or not. Or convergent or divergent, sorry. And so the question I chose for this is 329. Since the root test is brought up here, I thought this would be a pretty formidable one since it looks pretty complicated. it is a sub k equals, in parentheses, 2k squared minus 1 over k squared plus 3, close parentheses, all raised to the power of k. So since we are using the root test for this, what I'm gonna do is I'm pretty much just gonna rewrite this in terms of n. I don't think that matters. A sub n equals, in parentheses, 2n squared minus 1 over n squared plus 3 raised to the power of n. And then from here, we're doing the root test. So we take the square root of all of this, the square root of the absolute value of all of a of n. So we would do, let me write the limit equation, limit n approaches infinity, and the nth root of the absolute value of a sub n. This equals limit of n goes to infinity, the nth root of absolute value of 2n squared minus 1 over n squared plus 3 squared. So far I have this, and all I've done is just put it into that root format, because now what we can do is we can actually remove that nth root, since we can actually remove that nth root since we're taking the root of that entire equation to the power of n. So we're just gonna remove that root, we're gonna cancel it out, and we're gonna rewrite it so that it shows that 2n squared minus 1 over n squared plus 3, and we still need the absolute value of that, and we just try to simplify this down, I believe. After this, there's an n squared, so n squared factored out from the top is 2 minus 1 over n squared. Yeah, n squared times 2 minus 1 over n squared, and then this is same thing, n squared times 1 plus 1 over n squared, no, 3, sorry. So it's just the same thing, n squared times 2 minus 1 over n squared, all of that over n squared times 1 plus 3 over n squared. We cancel out the n squareds. We're just left with 2 minus 1 over n squared, all over 1 plus 3 over n squared. And I believe the last thing left to do is well, what we just did, that actually equals p, which is you take the limit of all of this, and that equals p. So 2 minus 1 over n squared over 1 plus 3 over n squared. That's actually, we're trying to find the limit of n goes to infinity of 2 minus 1 over n squared over 1 plus 3 over n squared, and two. I believe it's just 2 because you have 2 minus a term over 1 plus a term, so you can essentially just, like, the p is just equal to 2, which is greater than 1, so the series diverges. So this is my work. The root tests and ratio tests are pretty useful in quickly figuring out whether a series converges or diverges. And yeah, I think I did this right. I might not have simplified correctly, but I do believe the series diverges. And again, 5.6 was quite literally a summary of all the series tests, series or tests, and when to apply them, what form an equation should be in for you to apply them, what conditions you should ideally check on the series before choosing a test to apply, and I hope I explained the differences between when to choose them pretty well. Again, an alternating series test, that's very specific to one form of a series, and if it's in the form -1 to the power of n, always use the alternating series test. Everything else, it's fair game for the other tests, unless if you use the root or ratio test and your p-value equals to 1, that means you should probably use another type of comparison test. But yeah, if there are any other questions or clarifications that I could make, just let me know. And thank you. That is the end of chapter 5.